Now, because of the 1 to 4 turns ratio, those transistors have a force beta of 4. Now, the start circuit is composed of the 4-layer diode CR1238. Now, when the voltage across it gets to 32 volts, it will then collapse with practically no voltage across it. Part of that start circuit is C1242, and then if you follow to the right and up, CR1242. Now, as we first turn the instrument on, we get positive half cycles at the bottom of C1242 and begin to place a charge on that capacitor. As we do, it lifts through CR1242, placing a collector supply on Q1241. And then just as soon as the charge on that capacitor reaches 32 volts and CR1238 fires, we get a positive step then at the top of that 4-layer diode. That positive step couples through C1239 to the base of Q1241 and turns that transistor on. All right, we begin to pull current out of that series path composed of L1237, C1237, primary of the transformer T1210, and out of the 1-turn primary of T1230. The current is induced into the 4-turn secondary, driving current into the base of Q1241, and that transistor is on and saturated. Let's draw a sine wave of current. Now we're in the first quadrant of that sine wave. Just as soon as the series resonant circuit reaches its peak current then begins to decline. We're in the second quadrant of the sine wave. Now, just as soon as we reach zero crossing, we're going to detect that in the inverter control. We'll see that later. It places a high at pin 9 of U1275, which saturates Q1252. As this collector pulls down to ground, it turns on CR1251, CR1252, and shorts out that dual 30-turn secondary on T1230. So all of the current then from that transformer is shorted to ground. That removes any drive to the bases of either Q1241 or Q1234. Q1241 there turns off. Now that was at the time of zero crossing. The reverse current turns on catcher diode CR1241, and it supplies current during the third quadrant of the sine wave. Now current flow through Q1230 is such that Q1234 would be turned on were it not for the short on those two 30-turn secondaries. Now at a time dictated by the inverter control, we remove that short. Q1234 turns on, completing the negative half cycle of the sine wave. Now again at zero crossing, we place that short on those 30-turn secondaries, which turns off Q1234. Now CR1234 comes into conduction to provide the current at the start of the first quadrant of the second cycle. Just as soon as the short on the 30-turn secondaries is removed, the current in T1230 is such that it will turn on Q1241, and that's where we came in. Now, as I said earlier, a square wave appears across the series circuit composed of the series resonant circuit L1237, C1237, and the primary of T1210. Now that square wave can vary all the way from about 220 volts to about 365 volts. But the voltage drop across the primary of T1310 remains constant at about 95 volts or so. So the balance of the voltage appears across that series resonant circuit. Now the oscillator will always operate slightly below the natural resonant frequency of that series resonant circuit. Now if the line voltage begins to go up, we sense that in the inverter control circuit, we'll see that later, and slows down the oscillator by increasing the time that short appears on T1230. Now that lowers the frequency of the oscillator. We're then operating farther away from the natural resonant frequency of that series resonant circuit, and a greater voltage drop appears across that now higher impedance of that resonant circuit. But the operation of the regulator circuit maintains the voltage drop across the primary of T1310 at a constant potential. Now if something goes wrong with the regulator circuit, and the output from this circuit goes wild, and the voltage across the primary of T1310 gets up to about 110 volts, we utilize a shutdown circuit composed of Q1248 and VR1246 and the associated circuitry. Now with each positive half cycle at the top of the primary of T1310, CR1244 turns on and maintains a charge on C1243, charged to the positive peak value of that waveform. Now as soon as it gets to about 110 volts, it'll lift through VR1246, lifting the gate of Q1248, and it fires. Now the cathode goes up and the anode goes down. Let's take the cathode first. The positive excursion reaches over to the base of Q1246, saturates that transistor, and notice that it's placed right across the 4-turn secondary winding. And with that short present, the oscillator stops. Now that can occur during any part of the cycle, and under certain conditions can blow a transistor, but this is an emergency shutdown. You see, we drive the CRT high voltage circuit from this pre-regulated supply, and if it gets too high, then the CRT anode potential gets too high, and it gets up to 28 kV, then there's danger of X-ray emanation beyond government standards. So it's important that we shut this thing down before that occurs. Now in order to start it again, we must utilize the start circuit composed of CR1238, C1242, and so on. But we don't want that to happen immediately, so we hold C1242 discharged with CR1249, see up at the anode of Q1248. Now when that thing is shorted and the cathode is up, then the collector would be pulled down, which pulls through CR1249 holding C1242 discharged so that it can't start again. Now with the oscillator stopped, we have no voltage, of course, at the primary of T1310. CR1244 is off, leaving the charge on C1243. Now that holds Q1248 on. Now just as soon as C1243 discharges through R1243, at that time Q1248 resets, then C1243 begins to charge again through R1247. That turns off CR1249 and allows the start circuit to work once again. However, if the regulator still isn't working and we exceed the voltage at the primary of T1310, it'll shut down again, you see, to protect the CRT from that overdrive. Now C1249 provides current in through the shorted Q1248 to provide base current for 1246 to provide that short initially. Now just down below the oscillator and to the right there, R1236 grounds the cover which covers this oscillator, and C1236 returns any capacitively coupled currents from the cover back into the DC reference. Then off to the left of T1230, down below there is C1238. Now that picks up any capacitively coupled currents within the transformer, takes them off the center tap of that 30-turn winding, and returns them back into the DC reference. See, it's important that all of these currents get returned back into the inverter circuit, not allowed to get into the chassis. Now if you'll consult that little sine wave of current that we talked about earlier, you can see that the fastest rate of change occurs at the time of zero crossing. Now that information is picked off T1235. It's phase shifted just a little bit in C1235 so that the zero crossing arrives at the right time. That fast rise or fast fall is differentiated in C1275 and C1276. Now inside of the IC, at pins 10 and 11, are 2K resistors to ground, which forms part of the differentiating network, and then also diodes to ground, so that we use only the positive exversion of that differentiated waveform. Now by having two differentiating networks, one on either side of the transformer, we utilize both the positive and negative going zero crossing. So a positive going pulse, either at pin 10 or pin 11 at the time of zero crossing, actuates a latch. Pin 9 goes high, which turns on and saturates Q1252 as its collector comes down to ground, pulls down through CR1251 and CR1252, placing the short on transformer T1230 and turning off Q1234 or Q1241 as we discussed earlier. Now back to the inverter control IC. At the same time, it releases a pull down on pin 12, the IC, lower right hand corner there, and C1300 begins to ramp up towards 7.5 volts through R1300. Now there are three sense inputs to this IC. There's pin 13, which is a current sense. Now that senses the current of the inverter itself. Pin 15, which is a voltage sense, and it uses the 130 volt output from this inverter. Then pin 2, which is fault sense, or sometimes E balance, which senses any change in the 5 volt lamp supply, or the minus 17 volt supply, or the CRT cathode current, or the CRT beam current. The bridge rectifier takes the output from T1235 and supplies 7.5 volts and minus 2 volts to U1275. Now the current return for that supply is through those three diodes, CR12, 88, 89, and 90, and R1287 to ground. Now if the inverter current becomes excessive, then the voltage drop across R1287 gets large enough to pull down on pin 13, and that is the I sense that we mentioned a moment ago. Now let's look at E sense in at pin 15. Now we're sensing the 130 volt output from the inverter supply using divider R1292 and the inverter control pot R1293, R1294, R1296, and Zener VR1297 to ground. Now R1297 to minus 17 volts is just a pull down for the Zener. Now CR1294 is reverse biased during normal operation. However, if we lose the minus 17 volt supply, that keeps that divider in good enough shape so that the inverter control continues to operate. That keeps the entire inverter circuit from running wild. C1298 is just a filter to keep the Zener noise out of the regulator. All right, let's drop down next to pin 2, which we said was called fault sense. Now, for minus 17 there is just a supply. However, it would read any difference in that minus 17 volt supply. What we are interested in there primarily is that 5 volt lamp supply. We're sensitive to a plus or minus 250 millivolt change in that supply. Now that fault sense, or E-balance as it's sometimes called, is a bilateral input. That is, it senses a change in either direction from the 5 volt supply or the minus 17. Now the I sense from the CRT cathode through CR1306 reads only an increase or an excess in cathode current, and that's true with the current sense from the CRT anode. Now let's follow that line off to the right and up through Q1373. Now the CRT anode current literally flows through R1371. Now when that beam current gets up to 30 microamps or so, Q1373 will turn on hard enough to turn on CR1376 off to the left and begin to influence the fault sense input. Now at the same time, as the collector of Q1373 pulls up, it allows a pull up through CR1378. Notice the pull up there toward 17 volts through R1378. That goes into the Z-axis circuit on the logic diagram and limits the intensity, which is in effect reducing the beam current. Now there's about a 100 microsecond propagation time around that loop. Now let's start with the increased beam current in the CRT. It's then felt here through R1371. There's then a voltage drop across that resistor, which then must charge C1771, which turns on Q1373. As its collector comes up, then it goes into the Z-axis circuit, as I said earlier, and that corrects for the beam current increase. But that 100 microsecond delay allows for fast single-shot operation without current limiting. In other words, since this limiting circuit doesn't have a chance to react until a single-shot display is completed, then the CRT works full bore, so to speak, with full beam current. Well, let's go back to the inverter control IC. Pin 4. We take off from T1208 and supply a sine wave in at pin 4. Now that goes into the base of a transistor inside of the IC, and its collector is tied to pin 3. And as the positive excursions of the sine wave turns on that transistor and the collector comes down holding C1267 discharged. Now if we lose power, then pin 3 begins to ramp up. We'll get to that later. Now pin 8 is an inverter shutdown. Whenever that goes high, that shuts down the inverter to the point where it has to be started again with the start circuit composed of CR1238, C1242, and so on. Now a while ago we left pin 12 ramping up towards 7.5 volts at the time of zero crossing. Now to better understand the operation of this inverter IC, if you'll draw an NPN comparator on a piece of scratch paper, just return the emitters to an emitter supply. The right-hand base is tied to pin 12, where that positive going ramp is in progress. The collector of the right-hand transistor has a collector load resistor and goes to pin 9. Now there's also an emitter follower in that path, but that's all right. You don't need to draw it. There's also a latch connected with pin 9, which was initiated by the zero crossing differentiated pulse, such that pin 9 went high. Now the left transistor in this NPN comparator, let's tie the collector just to a supply, and the base essentially to pin 15. Now you recall that pin 15 is tied to a divider connected to the 130 volt supply, and a potential is set at pin 15. Now as the ramp begins to run up on the base of the right-hand transistor, pretty soon it will reach comparison with the DC level from pin 15. The right transistor will turn on, the collector will come down, pin 9 of the IC will go down and release the short on transformer T1230 and allow Q1234 and Q1241 to turn back on again. Now if the line voltage increases, then the 130 volt output would tend to increase, which increases the voltage at pin 15, and the voltage on the base of the left transistor in the comparator goes up, which means that pin 12 of the IC and the base of the right transistor would ramp up farther and for a longer period of time. So the off time for the inverter has been increased. That then lowers the frequency of the inverter oscillator. It's then operating farther away from resonance of the series resonant LNC 1237, and a greater voltage drop appears across that series resonant circuit, maintaining the constant voltage drop across the primary of T1310 and holding the output from the supply constant. Now on the left side of your comparator, draw two more transistors. Just leave the bases disconnected for the moment. Tie all the collectors together, tie all the emitters together. Now tie one of the bases to pin 13. I guess we need an inverter in that line, don't we? Because pin 13 will go down when we sense an overcurrent. The other base tied to pin 2. Now under normal operation, the pin 15 base will be the more positive, therefore it will have control. However, if we sense a fault in pin 2, now that could be a difference in the 5 volt supply, the minus 17, too much cathode current, too much beam current, then that transistor will take over control of the comparator. You see, its base would go higher than pin 15 base. Or, if pin 13 will sense a greater than normal inverter current, then the base connected through the inverter to pin 13 will become the more positive base, and it'll take over control. So pin 15 has control under normal operating conditions. Pin 2 or pin 13 will take over control only if they sense an increased operating current or voltage. Now if pin 13 senses an extra large current, such as from a shorted winding in a transformer, or perhaps a shorted filter in the secondary of the supply, something of that sort, it will then move to completely shut down the inverter. The same is true with pin 2, if it senses an extreme change there at pin 2. Now a third shutdown is in case we lose line voltage. We lose the sine wave in at pin 4. Now that's when we turn the power off, you see, or we lose power some other ways. Now, as we said earlier, as long as the sine wave is present, then C1267 is held discharged. Now, just as soon as we lose power, then pin 3 begins to ramp up. Now, it only has to go 600 or 700 millivolts to turn on a transistor, and that initiates the shutdown of the inverter. Now, whenever a shutdown has been signaled, either by pin 13, pin 2, or the lack of signal in at pin 4, then there's about a 10 millisecond delay while C1264 off pin 1 charges. Now, a hold down on pin 8 is released, and it's pulled up through those resistors and diodes. Now, at that time, CR1251 and CR1252 form a full-wave rectifier, providing a collector supply for Q1252 and Q1254. Now, part of the 10 millisecond delay in shutting things down is that we must charge C1254 before Q1254 can turn on. As its emitter pulls up, it turns on Q1252. Its collector pulls down. It doesn't quite saturate, but it turns off CR1256 and CR1259, leaving the charge on C1256 and C1259, which holds up the base of Q1254, holding that transistor in saturation. Now, under that condition, we've pulled down through CR1251, CR1252, placed a short on the transformer up above, T1230, and stopped the oscillator. In 250 milliseconds, those two capacitors will discharge, allowing Q1254 to turn off, which in turn turns off Q1252. The collector pulls up, that removes the short, and the oscillator can start again, but it must start using the start circuit. Now, if the overload which initiated shutdown is still felt, then there's a 10 millisecond delay, and we shut down again. So the inverter control, under the shutdown condition, turns the oscillator on for 10 milliseconds and off for 250 milliseconds. And that very low duty cycle can't damage any circuit. Now, the 10 millisecond delay in shutting down the oscillator when the inverter control senses an overcurrent or overvoltage is to mask a heavy current requirement when you first turn the instrument on. Now, that gives the thing 10 milliseconds in order to charge those capacitors with an excessive current. Now, in warm-up, the inverter control will shut down the oscillator 2 or 3 times while the filler capacitors in the secondary of this inverter circuit are becoming charged. Now, off the collector of Q1252 and Q1254 is a network composed of CR1253 and the Zener and C1253 to ground. Well, when Q1252 turns off, removing the short on T1230, that transformer tends to ring a little bit. When that point gets to 10 or 11 volts or so, then CR1253 and VR1253 turn on and place C1253 from the secondary of that transformer to ground to suppress that ringing. T1310 secondaries are very straightforward, just full-wave rectifiers and filters supplying the various voltages, and includes 2 windings that appear on the CRT schematic.